My name is Priyamvada Natarajan, and I am for curiosity-driven science. As an astrophysicist and a cosmologist, I co-lead the Yale Center for the Invisible Universe, where we conduct pioneering research on dark matter, dark energy, black holes, and neutrinos. From a very young age, I've been captivated by the elusive and the invisible constituents of the universe, particularly black holes. And I bet many of you are probably just as obsessed as I am about black holes. Black holes, as most of you are probably aware, were first proposed by Einstein in his general theory of relativity. Newton explained to us how gravity actually works, but Einstein explained to us what it is. He showed us that gravity is the interplay between matter and the shape of space. So matter in the universe causes distortions in space-time, which is sort of the four-dimensional fabric that we all inhabit. That is the universe. And compact objects like the sun, neutron stars, and black holes cause extreme distortions in the shape of space. Black holes in particular are special. Not only do they extremely distort space-time, they in fact create a puncture in space-time. This idea of black holes, though it was proposed in 1915 as part of his theory of general relativity, it took a long time to become real, so to speak. The scientific community rejected it for about 4 decades. And the reason for that is black holes have really bizarre properties. 2 of them, for instance, have to do with the fact that black holes encase a singularity. They are a place in the universe where it turns out that all laws of physics break down. There's a singularity in the middle, in that puncture where our understanding of the universe completely breaks down. Second, they actually have this region where not even light can escape. So understanding the role that they play in the universe has been tricky. However, over the past few decades, we have figured out a lot about what black holes are and what they really do, how they manifest in the universe. And this is where my own work comes in on the origin of the very first black holes in the universe. But before I go there, let me give you a little bit of an idea of what we knew about black holes and what we've known about them for a couple of decades. Black holes originate from the end states of stars. Massive stars live fast, die young, and leave behind a very glamorous corpse sometimes, the most massive stars in the universe. And they leave behind black holes, which are tiny and compact. But these black holes that are small black holes are the seeds from which the supermassive black holes that inhabit the centers of almost all galaxies, including our own, are known. And it turns out that the origin of these black holes is a big question, an open question, because we are finding them ubiquitously everywhere in the universe, with masses of 1 million to 1 billion times the mass of our sun, including in our own galaxy. So these are little red dots that the James Webb Space Telescope is rapidly revealing that contain a very actively growing black hole. So how did we figure out what black holes are doing in galaxies is by studying the black hole at the center of our own galaxy. And the mass of this black hole is determined by the motions of the stars that circulate around the inner parts of the galaxy. So the question is, how and when do these black holes form? And so my own work has resulted in trying to provide a new pathway for the formation of the first black holes, a pathway that kicks into gear very, very early in the universe. And it occurs from the direct collapse of gas in the very, very early universe. And this happens in a setting where you have a parent galaxy that has formed stars and has a satellite in which you form this direct collapse black hole. This object merges and it forms a very unique kind of galaxy, an overmassive black hole galaxy whose light is dominated not by the stars, but by the black hole that is growing in its center. So this is an idea where the formation of the first black hole actually bypasses the standard star that I just finished telling you about as the origin of the tiniest black holes. So these black holes from the get-go are a few thousand to maybe even 100,000 times the mass of the sun at birth. And this, therefore, gives them a head start and can explain the million and billion solar mass black holes that we are finding very, very early on in the universe in place. And this particular mechanism for forming the first black holes has very, very unique signatures, as I mentioned. And these signatures we predicted in work done with my postdoc about 15 years or so ago, that they should be detectable both by the James Webb Space Telescope as well as the Chandra X-ray telescope. And of course, I've been very fortunate that the James Webb Space Telescope has indeed detected these objects. And it's a thrill to be around and within one career lifetime to have had the fortune of making predictions that were testable, have been tested, and have been validated. So one of the unique features of direct collapse black holes is the signature of their formation is carried in this very specific relationship between the mass of the black hole and the host galaxy, the properties of the host galaxy that contains it. And so these predictions are made not just in the infrared that the James Webb Space Telescope sees, but also in the X-rays detected by the Chandra Space Telescope. So it turns out now that we are able to peer really far back into the universe. And we are able to map all these invisible entities that shape our universe. And at this point, you might ask, why should you care? How does this impact your life, these abstract ideas? So it turns out that these monster objects in the universe, like this galaxy cluster, bend light as predicted again by Einstein's theory of general relativity, and the bending of light allows us to map the invisible. So there are these techniques, new algorithms that we developed, as you'll see, have come in handy for many other things. And black holes, for example, have a very intimate relationship with each and every one of you. You are carrying in your hands a smartphone, and you got here to Davos because the same equations that govern and explain black holes actually guide GPS. So we have this GPS technology today as a direct result of these fundamental, abstract, mathematically obtuse results that appeared to be not useful decades ago. So basic fundamental science always translates. And as I mentioned, some of the algorithms that we have used to render the invisible visible, connect the visible universe to the dark matter that is shaping it, those very image mapping algorithms are something you have encountered in your life very, very recently. And that has to do with MRIs and other medical imaging applications that have also come out of the work that's done in basic sciences. So science and technology come full circle, and translation happens, although it might take a little longer, and the path, the arc to the translation may not be really obvious from the get-go. So what I want to do here is to make a case for fundamental science and for funding of fundamental science, and by governments, by philanthropies, and by the private sector. Because the arc of science, the results and the scientific breakthroughs, and how they are going to transform our life is not something we can predict today. But history shows us that science and technology have fundamentally changed our life. And given the pressing global problems that we are facing right now with climate change, pandemics, there is no way out of funding basic science. Just stop here.
Wonderful. Thank you so much, Priya. Now you get to relax and sit down.
Thank you.
Oh.
Thank you, please.
I'm Max Tegmark, a physics professor from MIT. So it's such an honor for me to be here with one of the great rock stars of astrophysics and talk about one of my favorite topics, black holes. So to start off, just to make sure we were all on the same page and got this right here, is it fair to say that this basic mystery you began with is kind of like if you walk into a daycare center and you see this 6-month-old child that weighs 75 kilos. And you're like, oh my gosh, how did this child get so big so fast? And then we have this view that's been held by some astrophysicists for a while, that there was a black hole that maybe came from a dead star, and it was kind of gobbling up some other stars like popcorn, one star at a time. And when it eats these stars, it gets more massive and grows. And then you have this very interesting alternative theory that actually, no, it wasn't mostly popcorn or eating stars. It actually started out eating gas from the very beginning. So I'm very curious, this very dense disk of gas, which forms the black hole, where are we now, if you can unpack this a little more observationally, in actually seeing these or seeing indirect evidence of them?
Yeah, so I think you have an absolute apt analogy for understanding that the growth history, both the birth and the growth history of these objects, is very special and peculiar and non-standard. You know, you've done yourself some pioneering work on the very first stars, right? So here, you need a set of cosmic conditions and a couple of different settings. And there are many settings available in our universe where this can happen. And where basically you can form from direct gravitational collapse, so aggregating a lot of matter into a really tiny space in this very interesting, fairly commonplace setting. And the prediction is that the satellite where you form the direct collapse black hole will merge with the parent, and the parent has already formed stars. However, this object, which is an overmassive black hole galaxy, sorry for the slightly unimaginative title, would actually glow, and the emission that you would get from it would be dominated by accretion onto the black hole and not from the stars. So we predicted this in 2017 with detailed spectral predictions and the ratio of energy.
Just so I understand, are you talking about the accretion that happens after it falls into the bigger galaxy, or are you talking about when it formed initially?
When it forms, both. So accretion is what governs everything. Mm-hmm. It's when it forms as well as once it merges with the parent galaxy. So the first object that James Webb detected that really matched all our prediction, and there were 7 predictions, detailed, both the spectral shape, the amount of energy that comes out in the infrared that James Webb should detect, the amount of energy that comes out in the X-ray that Chandra should detect. So there was an object UHZ1, which was in place about 10 million times the mass of the sun already, when the universe was barely 470 million years after the Big Bang. So it's extremely early. And there is no way, without huge amount of fine-tuning, that you could start with a stellar remnant black hole and grow it up that rapidly.
Yeah, just to clarify, our sun is going to go for a total of 10 billion years or so until it dies. And even the stars that, as you said, live hard, die young, the most massive ones, they might need quite a number of millions of years before they start their death process. So this is crazy fast.
And so there's been this one object. These are very faint. I mean, this is so far away, it's really faint. And that's where sort of, my interest in mapping dark matter and black holes kind of collided in a fortuitous way, because we were able to see this because these conglomerations of dark matter in the universe behave like magnifying glasses. They actually deflect and focus much like the magnifying glasses that we use. And this faint object happened to, and this was therefore a gift from the universe, right behind a very strong magnifying glass that brought it into view. Otherwise, we may have never seen it. And there are many other candidates now which have the similar properties to UHZ1 and seem to be kind of, very aligned with the idea of having direct collapse as the origin for the central black hole.
Great. So for reference, raise your hand if you have kids. So that kids tend to be pretty messy eaters when they're little, right? You try to feed them, but a lot of the stuff come flying back out again. It's sort of fortunate that black holes are messy eaters too. So you might think seeing a black object on a black background is just completely impossible. That is indeed one of the reasons Priya has to work so hard to find the black holes. But when they eat stuff, gas, for example, a lot of stuff comes flying out. A lot of X-rays and other kinds of photons and various other things. So this, can you say a little bit more? Is most of the data that you have, which has been conveniently magnified and you can see, is it mostly data on what the black hole is doing after it's fallen into this bigger galaxy, or is it mostly from this very gas-dominated little birthplace that it had?
So the birth itself happens extremely rapidly. So catching something in action while it's being born is really quite hard, practically impossible. So what we are really seeing is after this overmassive black hole has formed from direct collapse, and it ends up kind of in this parent galaxy in a very transient state. So most of the black holes in our universe, including the one at the center of our galaxy, do not outweigh the stars. The stars outweigh the black hole by several orders of magnitude. And this is completely the opposite. And so that's a transient phase that these galaxies then snap out of, because the stars start to grow and assemble, and we reach where we are now with most galaxies.
So after first having a diet of almost all gas where it gets born, it falls into this bigger galaxy, and it's still eating a diet of mostly gas, not so much popcorn or stars, because most of what's there is gas.
Yeah,
makes a lot of sense. Yeah.
And I think, as you mentioned, right, one thing to clarify is a lot of the light that we're seeing from the black hole, right, is gas that is being pulled in and gobbled by the gravity of the black hole. Hasn't quite crossed the event horizon yet, because remember, we are not going to get any signals once you cross the event horizon. So everything that we are seeing is from gas that is being sped up close to the speed of light, and it gets really hot and it starts to glow. So that's the light. The dying gasps of gas are what we are seeing that's revealing the presence of this black hole.
Great. So it's interesting. Black holes, I feel, have gotten a reputation as kind of the bad guys of the universe. They're scary, they eat things, you can't come out afterwards, and so on. You mentioned that there are also good things, first of all, about studying black holes, because this basic science we learn can be used for all sorts of great technology here on Earth. But I wanted to ask you if they've also gotten an unfairly bad reputation in a more direct way. We see that pretty much all galaxies have a big black hole in the middle. Do you feel that the role they play in regulating star formation and so on is ultimately also helpful? Like, for example, do you think that life on Earth would have actually happened in the first place if there were no black hole in the middle of our galaxy? Or
No, I think that's a great question. I think aside from the fact that, there are all these downstream practical applications, black holes are really enigmatic because in many ways they also represent the edge of what we can ever know. They're the edge of knowledge. So they're limits of what the human mind can really figure out. But originally, black holes were thought to play a really marginal role in galaxy formation. But I think in the last 2 decades or so, we've understood that they are actually fundamental to shaping the visible matter in galaxies. So one could say that we may not actually be here if there wasn't a black hole that had regulated, modulated the formation of stars in the Milky Way. And so I think now we believe that they play a starring role, from the margins to center stage.
So even though you don't want to fall into a black hole and get eaten and they're scary, you're saying in a way we owe our existence to black holes, because if there were no black hole in the middle of our galaxy, this area of space that we might have been uninhabitable.
That's right. I mean, I think we would not have had the stellar nurseries and the stellar distributions, and hence the planets around those stars that could have given rise to life as we know it.
All right, so thank you to the black holes for giving us an opportunity to have this conversation. And that was, well, we're not done yet, because I want to make sure that, okay, I hope the black holes heard this, are appreciative enough that they don't eat us. So I want to give you guys a chance to ask any fun black hole questions that you have. Let's start over here.
Hi, Luc Melis, Amsterdam. I have a question. Did all your vast research and knowledge give you any insights or a different opinion about us as humankind? Did it change your perception about who we are as human beings? And really curious to hear that.
Yeah, I think that studying cosmology in general and black holes specifically really instills a sense of cosmic humility, because why should we, who have an organ the size of a cantaloupe, a gelatinous thing out here, be able to figure all of this out and understand our place in the universe, and how this physical universe, which we have again the good fortune of looking back in time, looking out into the universe, is uniquely allowing us to look back in time and piece together this beautiful cosmic story that we are part of. So I'm a bit of a romantic. So for me, it's just really moving that we have these capacities. And I feel really grateful and humble to be alive at this time when you have all these convergences of, the sophistication of human ideas, our skill in building technologies, and the collision of these sort of ideas, instruments, computation that allows us these insights at this time. Yeah, I think that it makes you feel very grateful and humble.
Yeah, but not just humble, I think also empowered, because I feel we humans have been the masters of underestimation, right? Not only did we underestimate the size of our cosmos and our opportunities, again and again making the mistake of thinking that everything we knew of was everything that existed, just to find that that was just part of a much grander structure, a planet, a solar system, a galaxy, a supercluster, a universe, etc. But we had also underestimated our own minds and our ability to understand. Black holes, right, were not arguably discovered first with a telescope, but with a pencil. People like Einstein and Schwarzschild and even Laplace, right? And the idea that by thinking with these brains that had been evolved to pick bananas and so on, we could unveil.
I know. I think, it's this weird, as you said, simultaneously feeling very significant and insignificant at the same time. Significant because of these capacities that we never even imagined. I don't think Copernicus, for example, would have ever even imagined in a hallucinogenic, dream state that we humans would make these satellites, the Voyagers, that would actually leave the solar system, because at that time, the solar system was the universe, right?
Yeah. Absolutely. So never underestimate yourselves.
Right.
And then we have a question on this side here, and then we'll go to Jean after that. Yeah.
Hello, thank you. Thank you for the interesting talk. I really like it. So I liked also the analogy of the big baby, you know. So my question is, does this baby get old? I mean,
Yeah.
do they grow forever or do they evaporate at some point? And then if it is so, then is it possible that then when we see them, they are already gone?
Great point. Yeah, so it turns out that our current understanding informs us that galaxies and black holes grow in tandem. And yes, they do grow to enormous sizes and masses. So the most massive black holes in the universe, in the nearby universe that we've detected, are tens of billions of solar masses. Yeah, and in fact, many people, including myself, have speculated on, is there physics that could set an upper limit to how big a black hole can really grow in a galaxy, confined in a galaxy. So it appears that they're extremely coeval in how they evolve, galaxies and black holes. And for the second part of your question, could you just repeat the second part of the question? Oh yes, because when we look out into the universe, we are looking back in time. So for example, light takes about 8 minutes to come from the sun itself. And these objects that I showed you, the little red dots, they're billions and billions of light years away. So what those galaxies actually look like today and what those black holes are doing today, we don't know. We just know what they look like when light actually left them billions of years ago. As for evaporating black holes, Stephen Hawking suggested that very, very early in the universe, right after inflation, you could form these distortions, these punctures in space-time. Those are referred to as primordial black holes. But these black holes would evaporate over time with Hawking radiation and would completely disappear. However, that for black holes that we have been talking about, these supermassive black holes or even stellar mass black holes, it would take more than the age of the universe for that to happen. So these monsters are basically here to stay. However, depending on what the other invisible driving force of the universe is and its true nature, dark energy. We don't know what dark energy is. So with all these dark entities, we know how they manifest in the universe. We don't know what they really are. It's quite possible one of the outcomes, so dark energy determines the ultimate fate of our universe. One of the outcomes, potential outcomes, is that we could all end up in a big black hole. There could be a big crunch.
Yeah, so we can add that to another cool feature of black holes. They're the long-term rulers of our universe, because after they basically eat all the food in their neighborhood and stop growing, they just hang out there for a ridiculously long time while all the stars burn out and so on. So the last laugh is
right. Yeah.
They get the last laugh.
Yeah.
Jean Javolis.
Yeah, so basic science, just so that we can understand, is more than enough. But at the heart of almost everything we do now is quantum physics, right?
Yeah.
And Max referenced that maybe there are applications here on Earth. After this big crunch thing, I feel ridiculous asking this question, but what might be some of the applications that come out of our advancing knowledge about black holes that have applications like quantum mechanics at the heart of all computing?
So, as I mentioned, some of the applications we have already kind of harnessed, and that has to do with just understanding the nature of gravity itself. It gives us a deeper insight into gravity, and it's allowed us to launch satellites, do GPS, keep track of, time and space. So one other thing that we believe that we haven't quite understood as well is how the energy that is generated in the regions around a black hole, how the gas, for example, is transported over large cosmic scales, and the efficiency of that kind of energy generation process. So it could potentially in the future help us understand new ways, more efficient ways of converting mass into energy. So, the course of future science, basic science, is really hard to predict. So I can't quite tell you that if we find this and that's going to give you this. But what is a certainty is that we are going to find something, and that it is going to give us many, many unimagined possible products and ways in which it is going to touch our life.
Yeah, I completely agree. And just to add a second way in which science really helps tech, there are two ways. One is the direct way. Einstein starts wondering about the theory of the nature of time, discovers E equals mc squared, and then later we realize we can directly use that to build nuclear reactors and give green energy, right? But another thing, which is I think even more impactful for technology, is scientists get obsessed about some seemingly weird question. And in order to study that question,
not referring to me, right?
the scientists develop technology that would otherwise not have been developed, which turns out to be super useful. Let me just give a black hole example. So there's been a huge effort to build a black hole telescope called LISA, which measures gravitational waves, ripples in space-time of a wavelength roughly the size of the inner solar system. The idea sounds like science fiction. You put 3 satellites orbiting around the sun, and you send laser beams between them, and then you can measure very carefully what's going on and be like, oh, space got warped here. There must be, maybe there's a black hole over there. No normal venture capitalist would be developing technology for how you can point a laser super accurately from one fast-moving satellite to another fast-moving satellite far away. But this was developed to study black holes. And then Starlink is using exactly that technology. So when you invest in basic science, the returns that has for society is not only from the scientific discoveries, but I think even more often, you get these crazy returns to society from the tech that the scientists discovered to study these questions, which people otherwise wouldn't have developed at all. So we're out of time here, but I hope Priya has convinced you not only that black holes are very cool and not only scary, but also very helpful for us. We might not have this conversation if there weren't for the black hole in the middle of the Milky Way, but also that more importantly, that society's investments in basic science are arguably the highest ROI investments we've ever done. So thank you so much again, Priya.
Thank you so much, Max. Thanks everyone for coming. Bye.